Next, we move to a really interesting project looking at um, American BioCarbon Bagasse Biochar. Here in the United States, we don't spend too much time looking at biochar from agricultural residues. China's making a couple 100,000 tons a year of biochar from wheat straw and corn stover and so on. But Erwin is dedicated to bagasse, so tell us your story.
Yeah, good afternoon. My name is Erwin Bogner. I am the Chief Technical Officer of American Biocarbon and kind of founded the project for American Biocarbon. It was quite amusing yesterday when I met Tom Miles for the first time, and he said to me, "Ooh, American Biocarbon, the forever project." And he was right. So I will give you a little bit of a background of American Biocarbon first. Let me first switch to there we go. I'd like to give you a little background on American Biocarbon. So what we did is basically about, believe it or not, this started in 2013. We were looking at a project in Louisiana to make pulp, paper pulp out of bagasse. And this was the time when we realized that there was just an immense amount of bagasse available that the sugar mills did not know what to do. What happened is, with all the natural gas issues they had, and after Katrina, all the bagasse that the sugar mills were producing, there were no off-takers. There used to be a company was called Silodex that was making ceiling tiles out of it, and Katrina put them out of business. And all of a sudden, after, around every sugar mill in Louisiana, huge mountains of bagasse started to appear. And we looked at it and said, wow, what an opportunity, right? So if you have a lot of biomass in one spot that is of very consistent quality, actually, right? And it's a renewable material that comes every year from the sugar mill. So we get actually in that sugar mill, we get in the neighborhood of about 150 to 175,000 tons of bagasse annually. So what we basically did, we said, we ought to do something with it, right? So, and initially in those days, in 2013-14, torrefaction was a very sexy thing. So we were looking to do torrefaction, make torrefied pellets out of it, and go into the energy market, right? The issue is always, if you do a project, 4 legs of a stool: raw material, technology, offtake, finance, right? One is missing, you don't have a project. So we had a raw material supply. We had offtakes that we were able to create, but technology was an issue. So we went to different companies and we settled with one company on the torrefaction technology. We raised a whole bunch of money, purchased a pilot plant that we installed at the facility, which you're normally supposed to do when you do projects like this. And after about a year and a half and a lot of explosions, right, we realized that this technology was not scalable, right? And this is the reason why financiers like to see pilot plants. The technology was just designed in such a way that you had to heat syngas indirectly with a heat exchanger. It was a disaster. So what happened is, at that time I exited the project, and the investment group of New York was working with the technology provider and was trying to make that work, from 2015 until 2019, spent an additional $48 million, and were not able to make the project work. And even in 2015, my co-founder, Rick Buer, I'm sure you know him well, had the foresight. He looked very heavily always into biochar, right? And he always was saying, biochar, who will buy biochar? How do I get something financed with biochar? That was the issue, right? It's great, you have a raw material, but if I make, with the raw material we have available right now, we have over 2 million tons of raw material already stored, and annually coming an incredible amount at us. What are we gonna do with it? How do we sell it, right? So what happened is in 2020, we bought with another group the American Biocarbon project back and created a biochar project. So the belief and the basis for us, where we said, why bagasse, right? We ran tests. Material is very consistent, bit high in ash, but has incredible properties to make biochar. The porosity of it creates an incredible biochar. And in a couple of slides, I will show you actually microscopic pictures of it. So it really lends itself well in a lot of different applications, but especially in applications for soil amendment. We did tests in Louisiana and in Mexico and Guatemala, all over the place, where we were proving that application of biochar could increase the yield on a sugar field up to 30% per acre, with single applications that is basically impregnated with microbes. So that by itself, all of a sudden, did create a market, right? So what we did then, in 2020, we took this torrefaction facility, took it completely apart, and modified the torrefaction system and built a rotary kiln type carbonization system, right? A closed loop with a dryer system, and of course, we also added to it pelletization. The downside, well, I don't know if it's a downside, the balancing side of producing biochar is that you have a tremendous amount of excess energy. You need a sink for it. You cannot just blow it in the atmosphere. You need to do something with it, right? And that was actually the basis of our project. So in order for us to move forward, right, we had now all this bagasse, we analyzed it, and if you get something for free, as you all know, when it says for free, it's never for free. It's not easy to store bagasse. It's not easy to handle it. It's not easy to make out of it a raw material that is actually usable. Garbage in, garbage out, right? So we have to do multiple treatments of the bagasse that's stored in the hills in order to dewater it, make sure that the consistency is correct before I actually enter into our process. That's kind of what the main issue is with bagasse. And, you know, if you talk to a sugar mill guy, the one thing we'll tell you is that bagasse is a bitch. That's the saying in Louisiana. And it's really hard to handle, especially on the wet side. When it's dry, wow, all of a sudden you can do all kinds of things with it. So basically in Louisiana, right, they have, you know, in the US, we have over 40 million tons of sugarcane is being grown, right? The amount of bagasse available is incredible. Just in Louisiana, they have 11 sugar mills, 14.5 million tons of sugarcane production, and about 4 to 5 million tons of bagasse is annually produced just in the state of Louisiana. Florida does another 15, 20% more. And that is why we saw this as just a great opportunity, because think about this, no front-end transportation. If you can take that out of the equation of building a biomass power plant, you're already from here to here. And secondly, biomass supply security. Who's got it? Anybody in the room? Nobody. We have it, because the sugar mill needs to get rid of it. They're actually begging us to take the biomass. So what we did originally, our biomass supply agreement was, we agreed to handle the biomass. That saved the sugar mill already $1 million a year. That's what it cost them per year to just dispose of the bagasse, bring it to landfills, spread it, whatever they have done with it. So the moment we moved on the property, the sugar mill was already, oh, this is awesome. So, but there was actually an interesting bit with this. Initially, every sugar mill can say to us, you can have all the bagasse you want. And then we came to them because, you know, you have a commercial contract, you want to go and create a long-term supply agreement. And all of a sudden, the guys was like, is this worth something? This might be worth a lot in the future. I cannot give you a long-term offtake agreement, right? So the only mill that actually was willing immediately to give us an offtake agreement was the Texas sugar mill that we actually doing our project at. So what we did there, at first, the Texas sugar mill said, you know what, great. You know, 3 miles down the road, there's a plot, you can put your facility there, and you can run everything. So, and then we found out something profound, right? We visited the various sugar mills and we asked them for the biomass. And they told us, you can have any biomass in a long-term offtake agreement except the bagasse. And we were like, what biomass? So now if you look at the sugar making process, right? The sugar making process, you have the stem, the leaves, the tops. The leaves and the tops don't have any sugar. So when the harvester runs through it, they are supposed to extract all the leaves and the tops and leave it in the fields, and they put it on fire. In Louisiana, they put 465,000 acres on fire every year. It is absolutely incredible. So, but these harvesters don't work really well. So about 30% per mass of the cane coming back to the sugar mill is trash, is those leaves, right? And what it does to the sugar making process, right? Of course, it's more volume. It's a volumetric crushing process. It slows the process down, right? And in addition, when those leaves enter the sugar making process, right? They actually come out in the bag in the form of bagasse with sugar in it. So we ran tests. If you detrash, the sugar mill actually can run about 8% faster. It makes 8 to 10% more sugar per ton of cane. So we were down at the sugar mill, so how about we detrash? That means we take that biomass out before it hits the sugar mill, right? And that's what we did. And at that moment, the sugar mill says, where you want to put your facility? So all of a sudden, we were allowed on the property, directly at the exit of the conveyor belt. We built a biomass system. There it is, see? This is the detrashing system, right? That can handle over 1,000 tons per cane, 1,000 tons of cane per hour, right? And we extract that biomass. So that cleans the biomass for the sugar mill and gives them an incredible increase in yield. So what that basically does, the sugar mill says, you don't have to pay us for the biomass ever, as long as you run that piece of equipment. So this is the basis of our raw material supply, right? So our system is then, of course, we installed the detrash already, 4 years ago. So what we are now, right now, we're in construction in the plant where we now in construction of all the raw material handling, and we are now in the next phase where we're gonna install all our technology for producing biochar and producing pellets. So we have at this point a pilot plant in operation that we are now running for about 3 years. We're producing 3,000 metric tons of biochar per year, high quality biochar, and up to 15,000 tons of pellets. So the pellets can be fuel pellet or absorption pellet quality. Bagasse, on an absorption pellet basis, can hold 5 times its weight in water. It's incredible. So it is great for chemical remediation. It's great in the oil and gas industry for fracking, animal bedding, you name it. And then, of course, fuel pellets. Fuel pellets, we have an equal energy content to wood, even with the higher ash. The only thing is when we sell long-term contracts, we have to give people a discount on the ash, because what these guys want, they just don't want ash. But what we did is we did secure offtake agreements with European offtakers where we can take they basically blend our product with the wood pellets, and therefore they fix the ash problem. So the 3 years of running this carbonization system, of course, gave us now the ability to trim it. We developed a new catalytic oxidation process with it, so we can run very, very low HC ratios. Our biocarbon has our biochar has pretty consistently carbon ratios above 70%. So it's a very, very consistent, simple product. Except when it's stored out in the big hills, it can, before we use it, it can have up to 80% moisture when it rains. That is the 5-to-1 absorption ratio. So we have to bring that material in, and we installed baling systems where we basically de-water it before we run the material into our facility. So the construction of the new commercial plant right now will give us the ability to produce 107,000 metric tons of biochar per year and 150,000 tons of fuel pellets. It's a pretty massive facility that we are planning. So how does our facility work? This is what it's all about. So you all probably watch football games. The quarterback by itself cannot win the game, right? It is multiple technologies proven technologies that have to be put in a certain sequence in order to make a project work. So what we did is we using commercially available equipment that we of course modify for our use with our vendors, but we create a system that is fully autoelectric and fully autothermal. And how does this happen? Number one, we have the Biomass Separation Unit, where we basically bring all the material together with biogas. Either we store it in a biogas hill or we bale it, right? And the baling is basically a dewatering process. Just on the biochar side itself, we bring on the front end almost 60 tons of material in per hour. So what we're doing then, as the material comes from the baler, we run it through a shredding system to break it up again. When you take wet bagasse and you compress it, it becomes so hard you cannot even drive a nail to it. It's unbelievable. So we break it up again, and then we're using belt dryers to dry it. A belt dryer, we can use low temperature waste energy to dry the product, right? Then the material is being sifted and milled. The reason we do a size reduction after the drying is because that gives us a very homogeneous carbonization, right? If you have a different sizing in the carbonization goes slower, and you don't have a very, very consistent outputs. And that's when your HC ratios swing all over the place when you do the project. And the key is also when you run the product, the biggest problem is on your carbonizer to push the amount of energy in a very short amount of time into your biochar, right? In order to get the core temperature above 435 degrees Celsius. That's when you finally reach the proper HC ratios, right? So the reduction of the material helps a great deal. And what also helps a great deal is do not enter the material dry into your carbonization system. The steam makes a tremendous difference. So you want to have about at least 10% moisture. You want the water to flash off. It helps you to increase carbon surface. It opens the biochar up, right? And it also gives you a much, much better energy distribution within the system. But the only energy you lose is actually the energy of evaporation, or the other energy is going to come back to you on the back end, where we use the flue gases to produce energy. So what we do after the carbonization, we close couple with the carbonizer, which is an indirect fired kiln system. We close couple a thermal oxidation system where we can do VOC destruction 99.8% and 96% combustion efficiency. We take the flue gases. Our system is going to have a 64 megawatt firing capacity, right? This thing is like 65 feet high and 20 feet in diameter. So what it does, we take those flue gases, we pass those flue gases, of course, over the carbonization system at a temperature of about 1,000 to 1,100 degrees Celsius. And our carbonizer, the shell temperature is maintained at approximately 750 degrees Celsius. And we have multiple tamper systems in place where we can control the heat zones, right? Because you got multiple heat zones in the reactor. First zone, most energy, because until evaporation is done, you will not carbonize. Evaporation takes most energy, initial carbonization, and then you need very high temperatures on the backside in order to get the core temperature of the biochar to your quality, right? So what we then do is we take those flue gases, we pass the flue gases, we combine the flue gases that go over the calciner with the flue gases that come from the thermal oxidizer and heat thermal oil. So the thermal oil is being produced at 310 degrees Celsius. We drive that thermal oil, we pump it to a ORC power generation system where we heat cyclopentane, right? And then we have a ORC power generation cycle. The cold side of the ORC needs to be cooled, and the exit of the cyclopentane is 130 degrees Celsius, so we create 120 degrees Celsius water that we bring to our belt dryer. And the belt dryer gives it back at 75 degrees Celsius. That's how we close the loop, right? So in this way, The system is completely autothermal and completely autoelectric. So the way we start the thermal oxidizer with natural gas, fire the ORC, bring everything slowly up, start feeding the carbonizer, and after that, all you gotta do is add material into the carbonizer and keep the carbonization in check. What we actually found, was really profound on our pilot plant, these things don't like to be turned off. So every time we turn it off, right, it's a nightmare. So you wanna turn it off, let it run for a year if you can, right? And then turn it off. I mean, this is really one of these things with all these systems. You need to make sure that you create a system that you don't have, that you can maintain while it runs. Don't bring the temperature ever down if you don't have to. That's kind of how we look at making good, proper biochar. So what is the basis of ours in terms of energy balance, right? If you take carbonization of sugarcane bagasse, you got the high heat value of bagasse pretty consistently is about 5.38 megawatt hours per metric ton, right? We produce the biochar pretty constantly at about 28 gigajoule, which is around 7.8 megawatt hours. So then we're gonna basically take this, create about 9.2 megawatt hours in syngas. We have about 1.4 megawatt hours of combustion losses. Everybody has those, unfortunately. We can, per ton of biochar produced, we can make 1.3 megawatts of electricity, and we have 1 megawatt we have to circulate at any given time to maintain carbonization if you want to do a single ton of biochar, and you have about 5.5 megawatts available for drying and excess energy. That is the basis of our system. And so this way, we basically can scale it straight from 0 to the 10 tons an hour that our carbonization system is capable to produce. The only reason we can do this type of system is because we have the material available. Raw material is everything, right? So what we're basically doing is we can now create 100,000 tons of biochar. We do not sell the biochar at less than 30% moisture, number one. We don't store it. I can tell you some stories about some fires. You don't want to go there. So the stability of the biochar is everything. And also our system, what we plan in our facility, we plan to sequester the biochar directly in our facility, blend it with everything else, so we don't have to worry about the backhand transportation. But we have carbon contents of 70%, hydrogen carbon ratios below 0.4, and very, very high surface areas. This is what the difference is between wood biochar and bagasse biochar. There you can see the difference. So it has like this wonderful one honeycomb structure. So the absorbency of that, our biochar will hold about 3.5 times its weight in water, compared to wood, as you all know, maybe 2.5 times its weight in water. And that is what makes this biochar so unique, especially for soil amendments. So in conclusion, right, the advantage of our project is no front-end transportation, right? We go fully autoelectric and autothermal. We produce 60% excess energy and 30 electric energy and 30% industrial heat energy. So we must have a offtake of our electricity, and that's the only reason we produce pellets, because we gotta go somewhere with the energy. So now that makes our pellet production very, very profitable, because the biggest cost in pellet production is always the heat and is the electric energy required for pelletization, right? Then, of course, the water holding capacity makes an incredibly unique biomass plant. We basically say it provides the largest available low-income housing for microbes, right? So what happens is when you put compost in there, the microbes move into these crevices and it just creates a very, very good soil amendment, right? And what we're doing is we have, with carbonization, we don't do everything with temperature only. We have a catalytic oxidation process that gives us the ability to lower the hydrogen carbon content to almost zero, if necessary. But again, that's not always necessary. If I have a customer that wants to make asphalt, it doesn't. It's one thing. If I have a customer that wants to make, a soil amendment, is another thing. It depends what I do with the biochar. So, this our facility will be fully operational in Q4 2025, and we are of course fully Bureau certified. We have our pre-certification, and we're currently already selling corks coming off our pilot facility. Thank you very much.
Biochar.org appreciates the support of our sponsors, exhibitors, presenters, and attendees. We look forward to seeing you at our next conference in September 2025.